Hello everyone, and welcome to our channel, Mootechie. It's wonderful to have you here as we dive into a fascinating piece of everyday chemistry. Let's get started. Have you ever wondered why milk doesn't instantly curdle when you add it to your morning coffee? The answer lies in the world of buffers. So what is a buffer? A buffer is a special aqueous solution that maintains a stable pH environment, essential for many chemical and biological processes. It resists pH change when small amounts of acid or base are added. It's composed of a weak acid or base and its conjugate partner. Buffers are crucial for maintaining stability in labs, biology, foods, and industry. They work most effectively near the component acid's pKa value, and they're characterized by two key concepts: buffer index and buffer capacity. Now let's look at the formal definition. A buffer is defined as a solution that resists changes in pH when acid or alkali is added to it. Its composition is a weak acid, abbreviated as HA, plus its conjugate base, abbreviated as A-. Moving forward, let's understand how buffers actually work. The mechanism relies on a weak acid, HA, and its conjugate base, A-, existing in a delicate equilibrium. When you add acid in the form of H+ ions, the conjugate base A- absorbs these extra protons to form more HA. The reaction is H+ plus A- yields HA. Conversely, when you add a base like OH-, the weak acid HA neutralizes the hydroxide ions. The reaction is OH- plus HA yields A- plus H2O. The ratio of A- to HA determines the solution's pH, and most effective buffering occurs when the pH is within plus or minus 1 unit of the pKa. To visualize this, imagine a buffer solution at equilibrium. On one side, acid, H+, is being consumed by A-. On the other side, base, OH-, is being consumed by HA. The components HA and A- are constantly shifting to maintain balance. Next, we explore a key quantitative measure, the buffer index. The buffer index, symbolized by the Greek letter beta, quantifies a solution's ability to resist pH changes when a strong acid or base is added. The buffer index value is also called buffer value or buffer capacity. A higher beta means stronger resistance to pH change. It's calculated by looking at the change in the amount of strong base or acid added in moles per liter, divided by the resulting change in the pH level. Why does this matter? It describes the slope of the titration curve. The steeper the slope, meaning less pH change for a given amount of added base, the higher the buffer index. It's formally expressed by the Van Slyke equation. Beta equals dB divided by dpH. Its unit is moles per liter per pH unit. Now, let's relate beta to buffer calculations. The Henderson-Hasselbalch equation explains why buffers work best near their pKa. The equation is pH equals pKa plus log of the ratio of A- to HA. The critical point is that pH depends on the ratio of base to acid. Small additions of acid or base change this ratio slowly when the concentrations of both are high. The buffer index, beta, is highest when pH equals to pKa, which is where the concentration of A- equals the concentration of HA. As the pH moves away from the pKa, beta decreases. A practical lab method for approximating beta involves adding a known amount of strong acid or base, delta N, and measuring the resulting pH change, delta pH. So maximum beta occurs when the ratio is 1:1. Why does the buffer index matter so much? The buffer index, beta, serves as a critical predictive tool, quantifying how stable a solution's pH will remain under stress. It predicts pH stability during active use in chemical reactions. It helps researchers select the optimal buffer for specific experiments. It is critical for maintaining enzyme activity in biochemistry and medicine. It guides formulation strength and establishes safety margins. And it identifies the precise pH region where protection is maximized. This predictability allows scientists to calculate exactly how much acid or base a system can neutralize before failing. For biological safety, it ensures blood, tissues, and food products remain within the narrow pH limits required for life and quality. But what factors affect the buffer index? The buffer index beta isn't constant. It fluctuates based on specific chemical and environmental conditions. Total concentration is key. Higher concentrations of HA plus A- result in a higher buffer index. The buffer ratio is also crucial. Maximum buffering occurs when the ratio of A- to HA is 1:1. pKa proximity matters. Buffers are strongest when the system pH is close to the acid's pKa. Temperature changes can shift dissociation constants Ka, altering pH and beta. Ionic strength plays a role. High salt levels affect ion activity, shifting the effective buffering range. And dilution has an effect. While the pH may remain stable, the buffer index drops significantly upon dilution. There's a simple concentration rule. It's a direct relationship. More molecules means more capacity to absorb H+ or OH- ions. The sweet spot for any buffer is when pH equals to pKa. This is where the buffer curve is flattest and protection is strongest. Now let's apply this to a natural system. Beyond nutrition, milk is a complex chemical system designed to resist pH changes. Let's explore the proteins and salts that make this possible. The main buffering agents in milk are proteins, like casein and whey, and minerals such as phosphate and citrate salts. Coming up, let's solidify the concept of buffer capacity. Buffer capacity, beta, reflects the amount of acid or base absorbed before a significant pH shift. It is directly related to the total concentration of buffer components. Maximum capacity occurs when pH equals pKa and the ratio of A- to HA equals 1. Effectiveness drops rapidly as pH moves more than ±1 unit away from pKa. In a chart, a higher peak indicates stronger resistance to pH change, and the width of the peak indicates the effective pH range. A chart comparing buffer capacity versus pH would show one curve for a high concentration solution and another for a low concentration solution. The curve for the high concentration has a taller, narrower peak, showing it offers stronger resistance within a specific range. So what specifically in milk buffers to pH? The major buffering agents are several. Proteins, specifically casein and whey, are the heavy lifters. Their amino acid side chains accept or release protons. Phosphates exist in soluble form and bound within casein micelles, which are colloidal. Citrates are organic salts that chelate calcium and assist buffering near neutral pH. Carbonates from dissolved CO2 contribute a minor buffering effect. Why does this matter? Unlike simple lab buffers with one component, milk is a complex system where multiple ingredients work together to maintain stability. A pie chart showing the approximate percentage contribution to buffering capacity at pH 6.6 in fresh milk would be dominated by proteins, followed by phosphates, then citrates, and a small slice for others. Let's take a deeper look at protein buffering. Casein and whey proteins are major contributors, with caseins making up about 80% and whey proteins about 20%. They act as amphoteric polyelectrolytes. The mechanism arises from ionizable amino acid side chains that accept or release protons H+. Key amino acids involved are histidine, whose imidazole group has a pKa around 6.0, making it crucial at milk's pH, and glutamate and aspartate, whose carboxyl groups buffer in more acidic ranges. Casein micelles have a complex structure that allows binding of calcium and phosphate, creating a huge buffering reservoir. The isoelectric point, or pI, is around pH 4.6, where buffering capacity shifts as proteins precipitate, which we see as curdling. A diagram of a polypeptide chain segment would show various side chains acting as sponges for H+ ions. It would highlight an acidic group, like COO-, a histidine group with a pKa of 6.0, and a basic group like NH3+, all working together to stabilize the pH of milk. Next, we have the phosphate system in milk. Its primary buffer pair works via the equilibrium between dihydrogen phosphate and monohydrogen phosphate. The reaction is H2PO4- in equilibrium with HPO42- plus H+. Its effective range is great for milk because the pKa2 is approximately 7.2, making it very effective near milk's physiological pH of 6.7. Phosphate exists in two phases, a soluble form, which are free ions in the milk serum or whey, and colloidal form, bound within casein micelles as colloidal calcium phosphate. A dynamic equilibrium exists where changes in pH or temperature cause phosphate to migrate between soluble and colloidal states, effectively reloading the buffer. A distribution model would show the chemical equilibrium between H2PO4- and HPO42- happening across the milk serum, which is the soluble phase, and the colloidal calcium phosphate within the micelles. Now, let's discuss citrates contribution. The citric acid system is a tricarboxylic acid with pKa values of 3.1, 4.8, and 6.4. The relevance to milk is that the third pKa, 6.4, is very close to milk's natural pH, making it an effective buffer. Crucially, citrate acts as a calcium chelator. It binds free calcium ions to form soluble complexes. The effect of this is that it reduces free calcium, helping to solidify colloidal phosphate. This creates a synergistic effect where citrate works alongside phosphates and casein micelles to resist acidification. It's important to note that citrate levels fluctuate with diet and season, which affect fermentation rates in yogurt and cheese. A diagram would show the structure of a citrate ion with 3 carboxylate groups, COO-, and 1 hydroxyl group, and illustrate how it can bind to a calcium ion, calcium 2+, through chelation.
Why does milk's buffering matter in practice? It has a major industrial and biological impact. In cheesemaking, buffering controls the rate of acidification, which is critical for enzyme activity and curd texture. In yogurt production, the buffer capacity determines fermentation time and prevents the pH from dropping too quickly, which affects flavor. For heat stability, in processes like UHT processing, buffering prevents sudden pH drops that would cause protein coagulation and curdling at high temperatures. With coffee and other acidic foods, high buffering prevents milk from curdling instantly when added. And for digestion, milk neutralizes stomach acid gently, protecting the stomach lining and aiding nutrient absorption. An application overview highlights these key areas. Cheesemaking controls acidification rate and curd texture. Heat stability prevents coagulation during UHT. Acidic foods prevent curdling in coffee or fruit mixes. And digestion allows for gentle acid neutralization. Let's understand the milk pH range and its buffering strength. The pH of fresh milk typically ranges from 6.5 to 6.7. The high buffering zone, where it has the strongest resistance, is found between pH 6.0 and 6.8, thanks largely to phosphates and citrates. As bacteria produce lactic acid during fermentation, the buffering systems fight the pH drop until their reserves are depleted. The isoelectric point at around pH 4.6 is where casein proteins lose their charge and coagulate, leading to yogurt or cheese formation. Understanding these zones helps cheesemakers know exactly when to cut the curd and helps prevent milk from curdling in hot coffee. A graph of the buffering capacity profile would show the buffering strength starting at a baseline level, rising to a peak around the natural milk pH, and then decreasing as it moves towards the isoelectric point. How does milk compare to common lab buffers? Milk is a natural system. Its composition is a multi-component complex including casein, whey, phosphate, citrate, and minerals. Its effective range is strongest near its natural pH of about 6.2 to 6.8, but it shifts with fermentation. Its consistency is variable, changing with species, diet, season, and processing. Its primary use is in food systems, cheesemaking, yogurt production, and digestion. In contrast, lab buffers like phosphate or acetate are defined chemical pairs. They have a specific narrow effective range based on their pKa. For example, phosphate buffers around 7.2 and acetate around 4.8. They are highly consistent and reproducible due to controlled formulation. Their primary use is in scientific experiments, analytical chemistry, and calibration standards. The key difference is that lab buffers are designed for precision and specific pKa targets, while milk's buffer system is a biological adaptation for stability and nutrition. It's also important to know that milk's buffering ability is not static. Several factors can change its buffer capacity. Natural composition variations, like species, breed, diet, and season, alter protein and mineral levels. Component concentration is direct. Higher levels of casein, phosphate, and citrate increase capacity. Temperature and heat treatments like pasteurization cause denaturation and solubility changes. Dilution or fortification. Adding water lowers capacity, while concentrating milk increases it. Microbial activity during fermentation produces lactic acid, shifting pH away from the buffer's optimal range. And additives like stabilizers can artificially boost buffering power. Biological factors like genetics, lactation stage, and feed quality determine the baseline buffer components. Processing factors like heating, cooling, and concentration altered the physical state of salt and proteins. Finally, let's recap the key takeaways. On the theory side, buffer fundamentals tell us that buffer index, beta, quantifies resistance. Defined by Van Slyke, it measures how well a solution resists pH change, with a higher beta meaning greater stability. For peak performance, buffering is strongest when pH is near the acid's pKa and increases with the total concentration of buffering agents. And every buffer has a capacity limit. Moving too far outside the range of pKa plus or minus 1 drastically reduces its protective power. In application to milk systems, we see it's a complex team effort. Milk doesn't rely on one buffer. Proteins, phosphates, and citrates work synergistically. This natural buffering is critical for dairy quality, controlling fermentation rates and preventing protein curdling. And it's dynamic and variable, unlike standard lab buffers, shifting with temperature, processing, and microbial acidification. The final thought is this. Buffer index measures the potential to resist change. Milk is nature's brilliant application of this principle. Thank you for learning with us. We hope this breakdown of buffer index and milk systems helped clarify the chemistry behind the carton. Thank you. See you in the next class.